Welcome back to Neural Intel. Today, we're diving deep into some really fascinating work on generating digital avatars.
Yes, specifically cartoon avatars, but with incredibly detailed facial expressions.
You brought us a really interesting paper. It's titled GenEAva, Generating Cartoon Avatars with Fine-Grained Facial Expressions from Realistic Diffusion-Based Faces.
That's the one. And we also have details on their GenEAva 1.0 dataset and some related research. It's quite a technical piece of work.
Okay, let's try and unpack this. Our mission today is to really get under the hood of the GenEAva framework, understand the technical innovations.
Absolutely. We want to explore how it manages to create these, very nuanced expressions in cartoon form.
And see what their experiments actually reveal about how well it works.
Exactly. And, this isn't just some academic exercise. These cartoon avatars are showing up everywhere.
Oh, definitely. Social media, chatbots, even online tutoring I saw mentioned.
Video conferencing, VR, gaming.
Yeah,
They're becoming sort of central to how we interact online, offering a degree of personalization, maybe even privacy.
they really are. And I suppose the ability for these avatars to convey a wide range of emotions is, well, crucial for making those interactions feel more natural.
Precisely. But the researchers here point out that current methods often fall short.
In what way?
Well, existing data sets and techniques just struggle to produce cartoon avatars that can express the full spectrum of emotion, especially the more subtle stuff.
Right, so you lose that nuance. Makes sense. Imagine trying to show, like, mild surprise versus astonishment.
Exactly. It limits how useful they are in applications where that nuance matters. Think virtual therapy or even just characters in a sophisticated game.
Okay, that makes perfect sense. And expressiveness isn't the only hurdle they're tackling, is it?
No, the paper also digs into the challenge of identity memorization in these generative models.
Right. The risk that the model might accidentally spit out an avatar that looks uncannily like a real person from its training data.
Precisely. Which is a significant technical issue to overcome to ensure the generated avatars are genuinely new creations.
And they also mentioned something about biases in existing cartoon datasets.
Yes, things like skewing towards certain ages or races. They mentioned Manga 109 as an example. It highlights the need for more balanced data to train these things properly.
Okay, so GenEAva is positioned as a novel framework to tackle these technical limitations. What's a core idea?
It's basically a two-step process, which they illustrate nicely in Figure 1 of the paper. First, generate realistic faces with really fine-grained expressions using a diffusion model they've fine-tuned.
Starting with realism, okay?
And then step 2 is to stylize those realistic faces into cartoon avatars.
Interesting. And their definition of cartoon avatar is specifically the output of this process, derived from the diffusion model's generated identities.
That's right. The foundation is getting that realistic, expressive face generated first.
So let's dig into that first stage.
Yeah.
The facial expression generation model. You said it has two phases.
Correct. A fine-tuning phase and then an inference phase.
Okay, let's start with fine-tuning. What are they fine-tuning and what data drives that?
They start with a very capable text-to-image diffusion model, SDXL. Think of it as the base engine.
A state-of-the-art one.
Yes. And they fine-tune this engine specifically using something called the EMO 135 dataset.
EMO 135. What's special about that?
The 135 is the key. It contains 135 distinct categories of fine-grained facial expressions. That level of detail is pretty uncommon.
Wow, 135 expressions. That's a huge step up from the usual, like, 6 basic emotions, isn't it?
Absolutely. It allows for much more nuance, but to make sure the model actually learns from all these subtleties, they had to pre-process the data carefully.
What did that involve?
Things like using retina face for accurate face detection and cropping,
Yeah.
filtering out any images with watermarks.
Standard cleanup stuff.
Right. But also, crucially, creating a balanced subset of, I think it was 1,080 images. They made sure each of the 135 expressions was equally represented.
So the model doesn't just learn the most common expressions it sees. Smart.
Prevents bias towards, say, happy if that appeared more often in the raw data.
Okay, so they've got the balanced fine-grained data. What are the actual training objectives during fine-tuning? What do they want the model to learn?
Two main things. First, the standard diffusion model loss, which they call LDM.
Right, the typical loss that makes the diffusion models good at generating images by learning to reverse the process of adding noise. Equations 1 and 2 cover that.
Exactly. That keeps the model grounded as a generally capable image generator. But the second objective is the key one here. The expression loss, LEXP.
How does that work? How do you quantify expression accuracy?
They use another sophisticated model, an expression encoder called poster. It's designed specifically to recognize facial expressions.
Okay.
So the idea is to make sure the expressions in the generated images closely match the expressions in the real images from EMA 135.
Hmm.
They use poster to get an expression representation or fingerprint for both the real and generated images.
Like a numerical summary of the expression.
Pretty much. And then they calculate the mean squared error, the MSE, between these two representations. That's the expression loss, LEXP. Equations 3 and 4 detail that.
Got it. So poster acts as the judge, ensuring the generated expression matches the target. And these two losses, LDM and LEXT, are used together.
Yes, they combine them into one overall training objective, L, using a scaling factor, alpha, to balance their importance. Equation 5 shows this.
And they set alpha to 1.0.
They did, yeah, meaning both general image quality and expression accuracy were weighted equally in their setup.
Okay, so the fine-tuning teaches the model to generate realistic faces and nail those 135 subtle expressions. What happens at inference time? How do you actually use it?
During inference, you guide the fine-tuned model using text prompts, just like regular SDXL, but they put a lot of thought into crafting these prompts.
To get specific expressions and characteristics.
Exactly. High-quality faces showing that diversity of expressions. And interestingly, they actually used GPT-4o to help generate these prompts.
Oh, using an LLM to prompt an image model. How did that work?
They leveraged GPT-4o to systematically create prompts, ensuring a balanced mix across gender, a really wide age range teenagers, right up to elderly folks, and 7 different racial groups.
That's a deliberate effort to build diversity into the generation process itself.
Absolutely. The paper gives an example like a photorealistic face of a middle-aged Indian woman with shoulders visible, displaying a facial expression of delight, plain white background. Very specific.
That level of detail must be key for steering the model. And I assume they applied some quality control to the generated images.
Oh, yes. They filtered out results where the face was maybe too close, obscuring features, or if there were multiple faces in the image. Just ensuring a clean set of high-quality, expressive, realistic faces.
Right, so that's the realistic face generation covered. Now, the second step, turning them into cartoons. How did they approach the stylization?
They used a model called DCTNet for this.
DCTNet, why that one?
They chose it specifically because it's good at few-shot portrait stylization, meaning it can pick up a new art style from just a handful of examples.
Ah, so it's adaptable.
Right. And they noted its ability to keep the content details like the expression while changing the style, plus its general applicability. They use a version pre-trained for a specific 3D cartoon style.
So DCTNet applies the cartoon look, but it's smarter than just a filter because it tries to preserve the important stuff, like the expression and identity.
That's the idea. It synthesizes the image in the new style while aiming to maintain that crucial underlying information. They actually ran user studies to check if it succeeded.
We'll get to those. But this whole pipeline generates the final dataset, right?
Yeah.
GenEAva 1.0. Tell us about that.
So GenEAva 1.0 is the end result. It contains 13,230 cartoon avatars.
13,000.
Yeah, covering all 135 of those fine-grained expressions. And for each expression, they have 98 distinct avatar images.
98 per expression. Wow.
And critically, as we discussed with the prompting, these are balanced across genders, those 7 racial groups, and various age ranges. Figure 2 gives a nice visual sample of the diversity.
That sounds like a seriously comprehensive and well-structured resource.
Yeah.
The clean backgrounds you mentioned earlier probably help too.
Definitely makes them easier to use in different contexts. So they built this thing, but how well does it actually work? They ran several experiments to find out.
Okay, let's start with the core part. The facial expression generation. How did they test that?
They compared their fine-tuned model directly against the standard off-the-shelf SDXL, a clear baseline comparison.
Makes sense. What metrics did they use?
4 main ones: CLP score, Dino score, LPIPS, and a direct expression error metric they just called EXP.
Okay, can you give us a quick sense of what each one measures here?
Sure. CLIP basically checks how well the generated image matches the text prompt describing the expression higher is better.
Alignment with the text. Got it.
Dino looks at similarity in general visual features compared to real images of expressions. Again, higher is better.
Okay, general visual similarity.
LPIPS measures perceptual difference, things like texture, fine details. Here, lower is better, meaning more similar perceptually.
Lower LPIPS means closer perception.
Right.
And finally, XBIT, the expression error, uses that poster model again to directly compare the expression fingerprint of the generated image to the real one. lower error is obviously better.
So higher clip dano, lower LPI-P6 indicate success. What did did their fine-tuning help?
Significantly, yes. Their fine-tuned model beat the baseline SDXL across the board, higher CLP and dyno scores, lower LBIPS, and importantly, much lower expression error.
So the quantitative results really back up that their method is better at generating specific fine-grained expressions than standard SDXL.
Exactly. Strong evidence for the effectiveness of that expression-guided fine-tuning.
Okay, that's expression accuracy. What about the other big technical challenge? Identity memorization. How did they check if GenEAva was just copying faces?
They tackled this pretty thoroughly, using both quantitative analysis and a user study. The goal was to confirm the generated identities were genuinely novel.
Makes sense. What did the quantitative analysis involve? They used a standard face recognition model, ArcFace, to create identity embeddings, those unique fingerprints for all the generated GenEAva avatars.
Okay.
Then they compared these embeddings against embeddings from faces in their fine-tuning set, EMO 135, and also against faces from Celeba, which is a large celebrity dataset, likely part of SDXL's original training data.
Comparing generated faces to training faces using ArcFace, how did they decide if a match was found?
They calculated cosine similarity between embeddings and set a threshold. Based on their method, a similarity score above 0.68 would indicate the faces likely belong to the same person.
And what did they find? Did any generated faces cross that threshold?
Here's the key finding. None of them did. 0 generated faces exceeded the 0.68 threshold when compared to either EMO 135 or Celeba.
None at all. That's pretty definitive.
Yeah, and the average similarity scores were way below the threshold too, around 0.39 against EMO 135 and 0.47 against Celeba. It strongly suggests the model isn't just regurgitating training identities.
That's a really important technical validation for novelty and privacy. But they didn't stop there. They also ran a user study.
Correct. They wanted human perception confirmation. They took 50 random GenEAva images and paired each one with its most similar face from EMO 135 according to ArcFace.
Even if the similarity was low, they paired it with the closest one.
Right. And they did the same thing comparing another 50 GenEAva images to their closest matches in Celeba. Then they showed these pairs to people.
And asked them, same person or different people?
Exactly. The results. For the pairs compared against EMO 135, the data they actually fine-tuned on participants identified 0 matches. No one thought they were the same person.
Okay, so no memorization detected from the fine-tuning set by humans either. What about the Celeba comparisons?
There, they did find a small number of cases where people perceived a similarity.
Interesting. How did the researchers interpret that?
They suggested it likely stems from SDXL's original massive pre-training data, which includes many public figures from Celeba. So not necessarily memorization from their fine-tuning, but maybe some residual similarity from the base model.
That makes sense. SDXL has seen a lot of faces.
Yeah, and they mentioned they plan to potentially remove those specific similar faces from the GenEAva dataset and even look into unlearning techniques to further minimize any resemblance.
So overall, the evidence strongly points to the generation of novel identities, especially concerning the EMO 135 data. That's a key technical win. Now, what about the stylization? Did the cartoon transformation mess up the identity or the expression?
That's exactly what they tested in another user study, this time using Amazon Mechanical Turk AMT.
Okay, what did the AMT workers do?
They were shown pairs of images, the realistic face generated by the first stage, and its corresponding cartoon avatar from the second stage. Figure 3 shows the interface.
Sample comparison.
And they asked 2 questions. Is the identity the same? And is the facial expression the same?
Straightforward. Did they screen the workers?
Yes. They used experienced workers with high approval ratings. They sampled nearly 1,000 pairs and had multiple evaluators look at each pair, with control questions mixed in to ensure quality.
Sounds robust.
Yeah.
What were the results? Did people think the identity and expression were preserved? Figure 4 has the numbers, right?
It does, and the results were really strong. 96% approval for facial expression preservation.
96%. That's high.
And 93% approval for identity preservation.
Also very high. So people generally agreed that the cartoon version looked like the same person making the same face as the realistic version.
Exactly. It confirms that the DCT-net stylization method did a good job of translating the style without losing the crucial identity and expression details. They also mentioned plans to remove the few pairs that failed this check, further refining the dataset.
So the stylization holds up under scrutiny. Okay, one last comparison they did was qualitative against avatars generated by ChatGPT.
Yes, using GPT-4o and DALL-3, They wanted to see how GenEAva stacked up visually against a very advanced commercially available system when generating nuanced expressions. Figure 5 shows some examples.
What kind of expressions did they compare?
Things like compassion, desire, sympathy, jealousy. Quite subtle, complex emotions.
And what was the visual takeaway? How did GenEAva compare?
Well, looking at the examples, GenEAva seems to capture more subtle and, you could argue, more accurate renditions. For instance, their compassion avatar looks concerned, maybe a bit sad,
Okay.
whereas the ChatGPT one for compassion apparently had more of a smile, which might not fit everyone's interpretation.
Right, potentially misinterpreting the emotion.
Or for desire and sympathy, the ChatGPT results looked a bit more neutral or generic, according to the paper, while GenEAva showed clearer, though still subtle, expressions. Even jealousy seemed maybe more exaggerated, almost cartoonish in the ChatGPT version compared to GenEAva's more restrained take.
So the comparison suggests that even state-of-the-art general models like DL3, accessed via ChatGPT, struggle with rendering these really fine-grained facial expressions accurately.
That seems to be the implication. It highlights that achieving this level of nuance is still a significant technical challenge, and GenEAva's focused approach demonstrates a real advancement there.
It really underscores the specific contribution of their work in targeting expression fidelity.
Absolutely. It's not just about generating a face, but generating the right face with the right subtle expression.
Okay, so wrapping this up, this deep dive into GenEAva reveals, well, a pretty significant step forward, technically speaking. Creating these highly expressive cartoon avatars while tackling identity novelty seems like the core achievement.
I agree. The two-stage approach, the careful fine-tuning with that massive expression set, and the validation through experiments, especially on memorization and stylization fidelity, it's quite thorough.
And the GenEAva 1.0 dataset itself, with its focus on fine-grained expressions and balanced demographics, feels like a valuable resource for anyone working in this area.
Definitely. It provides a benchmark and a tool for future research. And that comparison with ChatGPT really drives home that nuanced expression generation is still an active research frontier.
So this leads to a question for our listeners to think about. How might these advancements in more expressive, potentially more private avatars actually change how we interact in digital spaces?
Yeah, from social media platforms to virtual meetings or even gaming worlds. Could this lead to richer, maybe more empathetic online experiences while addressing some of those technical privacy hurdles?
Something to consider. For those keen to explore the nitty-gritty technical details further, we definitely recommend checking out the original paper on Archift.
Absolutely. It has all the specifics on architecture, training parameters, more results. And looking into diffusion models, text-to-image generation, and facial expression recognition concepts would provide great context.
The references in the paper are also a great starting point for exploring that related research landscape. This was a fascinating look at GenEAva.